Hey everyone, welcome to today's session. Hopefully you can all currently hear me. So today we're going to be going through current in circuits. Okay, let's just check that we're all good. Okay, yes. Right, okay, so today's going to be a session on current and circuits, and we might as well just jump straight in. So let's do that. Okay, good. So just a little bit about me before we get started. I'm Matt. I'm the head of physics here at Snapprovise. I'm a physics PhD student, and also I'm a physics tutor and have been for the last 6 years or so. Okay, good. So let's get ourselves started. And what are we doing today? Well, we said it's current in circuits. More specifically, we're going to be understanding how to draw circuit diagrams and how to identify components by their symbols. That'll be in the first half. In the second half, we're going to understand how energy is transported around a circuit. And we're going to state Krokovs laws and use them to find currents. We're going to use them to find potential differences. And we're going to use them to find EMFs as well. Okay, good. So let's just see. Yeah, very nice. Okay, so let's start off by doing a little bit of a revision of the stuff that will be useful to know for today's session. So just some background knowledge, some words that we're going to be using regularly today. By the way, as I'm going through this stuff, if you have any questions, just put your question in the chat. That's no problem at all. And I might even ask some questions along the way. And as I ask questions along the way, if you have any guess at the answer, doesn't matter if it's right or wrong. It's good to be able to chuck your answers in the chat. And then I'll be able to see how people are getting on and if people are understanding. So, okay, great. Let's get started. So some things that we already know or things that it's going to be useful to be able to talk about today. Well, the first definition we're going to be using a lot is charge. So charge is usually given the symbol Q, and it's usually measured in units of coulombs. Okay, so let's write that down, coulombs. And the symbol for the unit, so the symbol for the quantity is Q, the symbol for the unit is C. So when we say coulombs, when we say how many coulombs something is, we'll say that number and then a C. Okay, good. So what is the point in charge? Well, charge is not something we really explain. It's something that we explain lots of other physical phenomena in terms of. So charge is like a really fundamental thing. So it's a kind of, we just take it to be a kind of intrinsic property of a variety of particles. Okay, good. And maybe just as we get going, let's remember there are some classic examples of charged particles, the kind of fundamental charged particles, at least before you get to subatomic physics, which are the protons and the electrons. Maybe the key thing to know at this point here is simply that the protons have what we call positive charge, and the electrons have what we call negative charge. We can actually give these numbers in terms of coulombs, and we'll be using those numbers as we go through some of the problems that we go through today. So in particular, the charge of the electron is minus 1.6 times 10 to the power minus 19 coulombs, and the proton is plus 1.6 times 10 to the minus 19 coulombs. Okay, good. So we have the stuff that we want to talk about. That's the charges. And then sometimes these charges are going to be moving around. And when they're moving around, we want to talk about how fast they're moving, how much charge is moving. And that's why we use the phrase current. So current is given the symbol I. It's measured in amperes. So amperes. And it's given the symbol A. So, okay, good. And it is a measure of the rate of flow of charge. Okay, good. Rate of flow of charge. And whenever you see rate of flow, that is secretly a mathematical definition hiding in words. So this thing here, rate of flow, That means, well, the rate means some change in time, rate of flow of charge. So it's the rate of change in charge with change in time. So E is, our current is the change in charge over change in time. Okay, good. Usually the cause of a current is motion of electrons and occasionally motion of other charged particles. So motion of ions. The most common type of electric current that you'll be asked to talk about, though, is a current that's caused by a flow of electrons. But it's not the only kind. Okay, good. So now let's talk about energy in electricity and energy in circuits. And to do that, we're going to introduce the EMF. Okay, so what is the EMF? The EMF is a new quantity. It's kind of like energy per charge. We measure it in what we call volts, which we give the symbol V. Okay, and it is the energy per charge given to charge carriers as they move through a component. Charge carriers as they move through a component. So the idea is that there are some components in circuits which can give particles energy. So we can imagine we have some charge and it's going through typically something like a cell or a battery. And as it moves through, it gains some energy. And the energy per charge that is gained moving through this component, that is the EMF. Okay, good. So whenever you see one thing per another, that's secretly a mathematical definition. So we can simply write it as energy per charge. Okay, the potential difference is pretty much the same thing, but just a different context. So EMF is about how much energy you pick up as you go through a component. Potential difference is about how much energy you lose as you go through a component. Now, you wouldn't usually lose energy when you go through something like a battery or a cell. So when we're talking about losing energy here, it's usually because we're going through something like a resistor. So here's a resistor. We have some charge that moves through the resistor. As a result, well, it's a resistor. It's hard to get through. You have to put in energy to get through it. And the energy per charge you lose as you go through this thing, that's the potential difference. So the potential difference V, again, measured in volts, and also given the symbol V, just like before, is the energy per charge lost as charge moves through a component. So it's just like EMF, but it's about losing energy rather than about gaining energy. And because of that, it has exactly the same definition at the mathematical level. It's yet again just an energy per charge. So is voltage the same as potential difference? Okay, this is a great question. Voltage is a unit. Potential difference and EMF are two kinds of things we want to describe in the world. So, okay, EMF is the energy per charge you pick up as you go through a component. Potential difference is the word we use for the energy per charge we lose as we go through a component. And both of those things are measured in units of voltage or units of volts. So voltage is the unit that you can use to describe EMF or potential difference. Cool. It's like meters are the units that you can use to describe height and width. They're two different things with the same unit, but the meter is just the unit. In this case, voltage is the unit, and the thing it can be used to quantify is stuff like EMF and potential difference. Okay, perfect. Good. Yeah, it's a really good question. All right, so I think at this point we're ready to get on with the main part. So that was the intro. Yeah, as always, do ask if you have any questions. Okay, it looks like we have a slight issue. There we go. Perfect. So here's the spec points. I'll just blitz through these because you can always pause or rewind if you want to check. So here are the spec points for the 3 main exam boards. And I think at this point, let's get going with the main section. Okay, so we're going to start by talking about and doing some exam questions on charge in circuits. So we're going to start by revising all the circuit symbols. Then we're going to cover Krokovs current law and do some questions. So to start with, let's take a look at this circuit on the left-hand side, and let's name these three main components. So let's call this component here 1. Let's call this component here 2. Let's call this component here 3. Let's call this component here 4. What are the names of each of these components? So for instance, in the chat, you could say number 1 is a cell or a battery. So what is number 2, for instance? And what is number 3? And what is number 4? So I'll put in number 4. Number 4 is a voltmeter. That is, it's the kind of thing that you can use to measure either EMF or potential difference. It's worth thinking about what it's measuring here. It's across a resistor. So here it's measuring the potential difference. If I put a voltmeter across here, it would be measuring the EMF. Okay, good. You're absolutely right. 2 is an ammeter. And an ammeter is the kind of thing you can use to measure current. And it returns amps, which is why it's called an ammeter. Okay, so we had one left, which is number 3. I think I may have even said it at some point by accident. So number 3 here is a resistor. And resistors are basically the kinds of things which it is hard to get current through. And when I say it's hard to get current through, it means you have to spend energy if you want to get charge through them. And that's why you measure a potential difference across them. All the charges that move through have to lose some energy to go through. Okay, good. So we have a load more here. So let's call this 5, 6, 7, 8, 9, 10, 11, and 12. Feel free to put in the chat any of these that you recognize. I will start with number 5. Number 5 here is like a break in the circuit you could choose to close, and that thing is a switch. Okay, any ideas for 6? Six is one of the ones I used to always forget, actually. Yeah, nice. 6 is a diode. Perfect. Good. Diode. Now, the next one looks pretty similar, so it wouldn't be weird if it had some kind of a similar name to the previous component. Yeah, LED. And LED stands for light emitting diode. This kind of makes sense. It looks like a diode, but there's some stuff being emitted from it. Turns out that stuff is light. Good. Okay, so number 8 here. So I'll put this one in. I haven't seen it in the chat yet. No, good. Okay. Number 8 here. No, you got it. Perfect. Thermistor. So that is a component whose resistance will change depending on the temperature. Okay, good. Number 9 here is a lamp or a bulb. Either of those words is fine. Okay, good. We have the, thanks very much. We have a variable resistor here. Variable resistor. Okay, so maybe it's not surprising from the name, it's a resistor, but it is variable. That is, it is a resistor whose resistance can be changed. You can imagine it's got some kind of a knob on it you can turn to change how hard it is to actually get current through this thing. Good, okay. Yeah, so whenever you see those arrows, they're a symbol of light, right? Because you're absolutely right. This is a light dependent resistor. So that's a common pattern you can see. Whenever you see these arrows, they're talking about light. Now here, the light arrows are going into this thing. So really what we're expressing is that something happens when light is received by the component. In particular, its resistance will change if you shine light on it. Does an LDR need a circle around it? I didn't think it did. I actually am not completely sure off the top of my head. Worth checking. If your textbook for your exam board is drawing a circle around it, then I'd recommend just drawing a circle around it anyway. But if you see a picture like this in an exam, you could interpret it as an LDR, whether or not there's a circle around it. It's clearly that component. Okay, it typically needs a circle around it. All right, well, let's draw that in. It can't hurt, right? There we go. Okay, good. Nice question. Cheers. Okay, finally, this one here is a capacitor. And I love this circuit symbol because it really actually looks like the thing it is. A capacitor is a pair of plates that you store some charge between. And by storing some charge between them, you get a kind of voltage across them. And that's really what this is. It's just like looking on the side of the pair of plates here. Okay, good. So capacitors are the kinds of things that can store charge. Perfect. In other words, they have capacity to store charge. Okay, perfect. So let's go on and start talking about Krokovs laws. Okay, so we're going to talk about both of Krokovs laws in this session. First half, we'll just talk about this one. Okay, and each of Krokovs laws is secretly not Krokovs law. It's a classic physical law that we're all familiar with, used in the context of circuits. Okay, good. So the conservation law that is secretly behind the current law of Kirchhoff's first law, as it's sometimes called, is that the total charge present in a circuit must be constant. Charge is like energy, and we'll come back to that later. Charge is something that you can't just create or destroy. It has to be conserved. If there was 5 coulombs of charge in the world, right now, there will be 5 coulombs of charge in a few seconds' time. That number can't change. Okay, that means if we keep track of charge in a physical situation, we can learn some stuff. So let's imagine we're looking at some part of a circuit here. So we've got some charge, let's call it Q. And this charge Q is over time going to travel towards this point where the wires of the circuit split. And so some of it is going to go this way at the later time, and some of it's going to go this way. Let's call the stuff that goes this way Q1, and the charge that goes this way Q2. Conservation of charge says whatever charge we started with, which was Q, should be the charge we finished with, which is Q1 and Q2. So conservation of charge simply says Q is equal to Q1 plus Q2. Now, the clever thing Kirchhoff thinks about in this situation is to say, well, rather than talking about some chunk of charge that's moving, I'm just going to talk about the rate of flow of charge. The amount of charge that flows into this node at any second will be the same as the amount of charge that flows out. And when you start talking about flows, you're talking about currents. So imagine I've got some current here. Let's do green for current. Let's imagine I've got some current here that's flowing into the node. I know that flow of charge, some of it's going to go this way, some of it's going to go that way, but it's all charge, and conservation of charge says the current that goes in should be the same as the current that comes out. So that's Kirchhoff's current law. Good, based on conservation of charge, current moving out. Yeah, exactly. Yeah, absolutely right. Good. Okay, cool. So let's take a look at some maybe clear examples of where you would see these things. Usually you don't just see a node that splits like this. Usually you get some kind of a circuit diagram. And let's imagine that we have some circuit diagram like this, and we're told we have some current going around here of size I. And we're told some of it goes through here, some of it goes through here. Well, let's call this I1, let's call this I2. Kirchhoff's law says, just as we were saying before, I equals I1 plus I2. That means, for instance, if we're told some of the numbers, like we're told this is 9 amps and we're told this is 6 amps, then we know what I1 is. So what's I1 here? So in currents involving parallel orientation could be example of a first law. Yeah, so we have, I think if I understand correctly what you're asking, here we have some parallel circuit stuff, which are often the stuff that you tend to think about voltage laws for, but you have nodes as well. whenever you have this parallel stuff, that means you have somewhere where the wire splits. So you have a few places where you can use this current law. I'm not sure if that answers your question. No worries. Okay, so we got 9 amps going in. We have 6 amps coming off over here. Conservation of charge says the other 3 must be going here. Good. Okay, so let's just state Kirchhoff's law very clearly and explicitly before we move on. Kirchhoff's current law states that the total current which flows into a point, so you can do this for any point that you spot, any node in your circuit, the total current which flows into a point is equal to the total current which flows out of that point. Current which flows out of that point. Perfect. Good. That's the current law. Okay, good. So with all that being said, that's the first half learning wise. We have some exam questions to go through, but first of all, how's everyone feeling? Is this making sense? It is. Could I say the same for voltage? There is something that feels a bit similar that I can say for voltage, and we're going to do that in the second half of the session. But when we're talking about voltages, we stop talking about points where wires split and we start looking for loops in our circuits. But we'll do that in the second half. Good. Yes, you're exactly right. Sorry to say, but the point is called a junction. Yes, that's true. I think you're right. I think it's more commonly called a junction. Good. Okay. Well, if there's any questions while we're going through these exam questions, just let me know. I think for now, we can just have a crack. Okay, good. So here's an exam question. We'll do a couple before we get to those voltage laws that people are mentioning in the chat. 2 6-volt torches produce similar intensities. The light source of one is a single filament lamp, and of the other is a combination of 4 light-emitting diodes. Figure 1.1 shows the IV characteristics of the filament lamp and 1 LED. Okay, so you'll always want to look out for when the examiner puts something in bold. That's probably going to be important because they're saying we're going to be studying these torches. We're going to be comparing some kind of a lamp with some kind of torch that's made of 4 LEDs. But they remind us the graph they've shown us is for 1 LED. So here we have a single LED. We have a graph of the current going through it against voltage. Here again for our, what's the other thing? The other thing is a lamp. We have a graph of the current against the voltage through it. Okay, good. So we understand the question. We understand the setup. What's the actual question? The LEDs in the LED torch are connected in pairs across the 6-volt battery and switch so that the potential difference across each of the 4 LEDs is 3 volts. And the first question here, okay, this is great news. It's a definition, and it's a definition we've already looked at today. The first thing asks us to define the term potential difference. Okay, cool. So I'm going to start it. Feel free to race me to it in the chat. The key thing to remember here is it stuff that we lose or is it stuff that we gain? Good. So you're absolutely right. It's energy per charge, but we always want to mention that it is the kind of energy per charge that we lose as we go through a component. Okay, so define the term potential difference. It is, or at least it's the amount of energy you need to get through a component. That's also fine. So it is the work per charge, energy per charge would also be fine. The work per charge needed for a charge carrier to move through a component. Looks like my writing's a bit big there. We've kind of leaked into the next question. That's no worries. There we go. We'll just separate them like this. Okay, good. So you're absolutely right. It's change in energy per time or work done per time to go through a component. Okay. Next, we're asked to use figure 1.1 to determine the current through each LED. Okay, so I guess we should take a look again. What information have we now been given? The potential difference across each of the 4 LEDs is 3 volts. So that's a thing we know. Each LED has 3 volts across it. Determine the current. Fine. So let's go back. We were given a graph of current against voltage. We know the voltage is 3. Where's 3? 3 is over here. Good. So then what's the current? Well, at this point here, when we have 3 volts, the current is 30. And always be careful with the units. They can often catch you out. This is not amps here. This is milliamps. Okay, good. So the answer here is 30 milliamps. Okay, good. Since Q charge equals I2, so the charge, yes, the current is charge per time. So the problem here is they didn't explicitly, they didn't tell us any information about charge or time. So we have to try and figure out the current another way. And we're just lucky here. They've told us the voltage. They've told us the voltage is 3 volts. And we were given a graph of current in the LED against voltage. So since they told us the voltage was 3 volts, we can just use the graph. And the graph said at 3 volts, we have 30 milliamps. Okay. Good. So in the next part, we're asked to sketch a circuit diagram showing how the battery, the 4 LEDs, and the switch are connected in the torch. Okay, so let's take a very close look at the question again. They're connected in pairs. Okay, so maybe we should draw our LEDs in pairs. So, okay, 1 second. We just need to fix something. We'll be ready in a second. LED, good. Okay, so we're ready to have a go at this. Sketch a circuit diagram. So notice that we're told that they are connected in pairs across, and there's 4 of them. So, okay, let's start by drawing our battery. Our battery is going to be something like this, and we're told the battery is 6 volts. And then we've got to connect them in pairs across. Okay, so here's our diode, but remember it's a light emitting diode, so we need to draw those arrows going away. Arrows going away. Good. Okay. And we're going to do the same here. We have our diodes. We have our diode. Remember, there's 4 of them all together. They're connected in pairs across the battery. So that's what we've drawn here. We've drawn pairs of diodes connected across the battery. And just as a little sanity check, do we agree that the voltage should be 3 volts in this picture? You're absolutely right. I really wanted, it would make more sense to draw it this way around. Thanks. Good. Does it matter how many cells you draw to represent a battery or any other power source? I'm not sure, but unless you have any particular reason to, it seems safest just to use 1 cell. Okay, good. Fine. So notice that we got 6 volts altogether, so we would indeed drop 3 volts here and 3 volts here. This is something we're going to talk about in the next half of the session more. Okay, secretly I'm thinking about a voltage law there, which we're going to introduce later. Okay, good. Let's do one more question, and then we'll move on to talking about voltage laws instead. So in this question, we're given the IV characteristics of 2 electrical components, a resistor, line R, and a thermistor, line T. Okay, so in part I, we're asked to state Ohm's law, and we're asked to use figure 2.2 to explain why component R obeys Ohm's law. Okay, so let's start off by stating it. It's not something we've talked about yet. So Ohm's law says that through a resistor, at constant temperature, then current is proportional to the voltage. In other words, V equals IR. Okay, we're asked to use the figure to explain why component R obeys Ohm's law. Well, if we look at R here, we have a straight line graph. And whenever you have a straight line graph between your Y variable and your X variable, that means that they are indeed proportional. And that's what we have here. And if we look at our Y variable here is the current. And if we look at our X-axis here is the voltage. Okay, good. So in figure 2.2, R is a straight line, which implies the current is proportional to the voltage, which is exactly what we said Ohm's law would be. Good, mathematically, V equals IR. Perfect. Really nice. Okay, so this question goes on. One more part. This is quite a nice question. A resistor and the thermistor can be connected to a variable voltage supply of negligible internal resistance in two ways, as shown in figure 2.3a and figure 2.3b. Okay, good. The voltage of the supply is varied in each circuit until the current drawn from it is 0.6 amps. Use data from figure 2.2 to explain whether EMF E of our supply is 3 volts in figure 2.3b. So there's a lot of references to different figures here, so let's just be careful. What are they asking us to explain? Why the EMF of the supply is 3 volts in figure 2.3b. Okay, 2.3b, they want us to explain why this EMF should be 3 volts, okay? So we don't care about this figure at all for the sake of this question. And what should we use? Figure 2.2. Where's figure 2.2? Figure 2.2 was on the previous page. This here, sorry, we didn't actually write it explicitly. This here was figure 2.2. My apologies. Well, I guess we mentioned it here. It's figure 2.2. Oh yeah, good. We actually did. Fine. Okay, cool. So we have to use this graph to explain why the voltage is 3 volts. Fine. Okay, so taking a look at this graph, taking a look at this figure, what have we been told? Well, we have been told that there is 0.6 amps here. Now, this 0.6 amps, remember that Krokovs law is going to be split between a current that goes through here, let's call it IR, and a current that goes through here, let's call it IT. And Krokovs law says the current through R plus the current through T needs to be equal to 0.6 amps. Now, let's see whether we can use this data to explain why the voltage should be 3. So let's go back to our graph again, where we were drawing these graphs of current against voltage. So why does it make sense that the voltage would be 3? Well, if we look at a voltage of 3, what is the current for each of our components? Well, for T, we can see that the current is this. And what is this? The current here, IT, is 0.2 amps. Instead, if we look at R, what is the current through it? Well, at R, the current is 0.4 amps. So altogether, let's go back now. Let's see if this makes sense. We've just seen that when the voltage is 3 and only when the voltage is 3, this is 0.4 amps and this is 0.2 amps. And now we can see why the voltage had to be 3. It's so that the currents altogether add up to 6, like Krokovs says they should. EMF should be equal to voltage since there is an internal resistance. EMF equals 4.5 volts. No, so I believe here, because of the reasons I've given, it actually should be 3 volts. At 3 volts, the total current between R and T together is 0.6 amps, which is what Krokovs law says it should be, because we know that going into this node here is 0.6 amps. Okay, so now we have to explain this. So when, and well, let's say this, when the EMF is 3 volts, then the current through T and R will be 0.2 amps and 0.4 amps. This is the voltage which allows Krokovs current law to be true. Current law to hold, since 0.2 plus 0.4 equals 0.6. Okay, so that's a perfectly good explanation. So at 3 volts, the graph tells us that this current here would be 0.4 and this current here would be 0.2. Therefore, it's at 3 volts that Kirchhoff's current law would be satisfied. The current going in is the same as the current going out. Okay, good. So we are now ready to take a look at the voltage law instead. Fine. Okay, and I said the current law was about conservation of charge. The voltage law, Kirchhoff's voltage law, that is about conservation of energy. Okay, so let's jump straight in. So maybe this is more familiar than the conservation of charge. The total energy given to charge carriers must be equal to the total energy taken from them. Okay, so we'll see this in an example. The law of conservation of energy says the amount of the energy should stay the same. We're going to think about this in the context of a circuit, and we're going to say whatever energy our charge Q picks up as it goes around our circuit should be the same as the energy that it loses as it goes around the circuit. So let's imagine, for instance, that we have an EMF E1 here, some energy that we pick up here per charge. We have an EMF E2, some energy per charge we pick up here. And then we're also going to drop some energy. We have some potential difference V1 here, some potential difference V2 here, and these are going to be places where we lose energy. The energy we gain must be the same as the energy we lose. So we expect that the EMFs, the things we pick up, should be equal to the potential differences, the things that we drop. Okay, so this is Kirchhoff's voltage law. We're going to state it, and then we're going to look at this example on the right-hand side. So Kirchhoff's second law states that, and I think this is what you're getting at in the chat. In any closed loop, and we'll explain what a closed loop is in a second. In any closed loop, the total EMF must equal the total potential difference. So the key thing here, something worth noting, is that this works for any loop. So if you look at this diagram on the right-hand side here, it doesn't just have one loop. It actually has a load of loops. For instance, it has this loop here. It also has, let's say, this loop here. But maybe easier to miss is that we can also treat this entire circuit as some kind of a loop. And Kirchhoff's law will be satisfied when we study any one of these loops. Let's see, you said the voltage across this closed loop remains the same. Yeah, I mean, I would phrase it like this, I've written it here. The total EMF is the same as the total potential difference. Or another way of saying it is the energy you pick up around a loop is the same as the energy you drop around the loop. I think that's what you're saying by the voltage in a closed loop remaining the same. Good. Okay. Questions typically state the Krokovs laws, or should we assume them unless told otherwise? You should assume them. These are things that you want to know. The examiner won't necessarily tell you that you should use them. You should be ready to use Krokovs law on any loop and to use Krokovs current law on any node. Okay, good. So let's imagine that we had some EMF here, E1. Then if we look at this first loop, this purple loop, we know we will drop some potential difference here, V2, but the size of this potential difference will be the same as the EMF because the energy we pick up is the same as the energy we lose. So if this is 5 volts, then this will also be 5 volts. And if we use the green loop, we can see the same thing for this potential difference over here. The energy we pick up in this loop is 5. And we never see this middle component now. We're going around the big loop. Here, we must drop it all across this one. So this is also 5. So that's where this law that the voltage on any branch is the same comes from. Good. Okay, perfect. So let's have a look at an example of how to apply Kirchhoff's current and voltage laws all together in one big diagram. So here we've got a big circuit diagram. And in this big circuit diagram, there are some numbers we've been told, and there are some numbers that we haven't been told. And we're going to go around, we're going to use Kirchhoff's laws to try and figure out all of the unknown variables here. Okay, so maybe let's start off by trying to figure out this thing here. This thing here is some potential difference across this bulb here. It's a V2. Okay, so how could we try and figure this out? Well, let's use Krokovs voltage law around this loop. If we do that, we see that the EMF we pick up is 24. That's here. Then what do we drop? Well, we drop this V2, and we also drop this potential difference across the bulb. And this potential difference across the bulb is 12 volts. So altogether, we can rearrange for V2, and we get 24 minus 12, which is 12. So this potential difference here is 12 volts. Perfect. Okay, so let's have a go at another thing. Let's try and figure out this voltage here. Okay, so this time we're going to take the big loop. We're going to go all the way around, and we're not going to think about the stuff in the middle. This is a whole loop. Let's look at the EMFs that we pick up. Well, we pick up 24 here, and we also pick up a V3 over here from this EMF. And that's the thing we don't know. And let's see what we drop. Well, we drop V2 when we go through this bulb, and we've figured out that that's 12 volts now. Also, as we go through this bit of the loop here, we drop 9 volts across this thing. And here's something kind of fun. If we rearrange here, we're going to get that V3 is equal to 12 plus 9 minus 24. And that's kind of funny because it's actually minus 3 volts. So what that means is that secretly, this thing is actually pushing the other way. Okay, cool. So when you get a minus voltage, it means that your cell is actually pushing the other way to the way it was drawn. Cool. So anyway, we figured out its voltage. That's great. It's minus 3. Now let's have a go at figuring out some of these currents. And I guess the big one here is this I1 here. Once we know I1, we know I2. They're in series, so they'll be the same. So let's look at this node here. What do we know? Well, coming in, we've got 9 amps here. And coming in here, we've got 6 amps here. The current going in is the same as the current coming out. So this must be 9 plus 6 amps, which is equal to 15 amps. In other words, I1, which is also the same as I2 over here, is 15 amps. Perfect. Okay, so hopefully that's making sense. How are we all getting on? So we have a couple more exam questions to go through, and then that will be the end of the session. Okay, flat face. Okay, cool. Let me know if there's any questions. You'll also ask me questions as I'm going through the exam questions. You realize there's something you find a bit weird. Okay, so I'll look out in the chat for any more responses. You're a bit confused with some questions. Okay, well, we'll go through some more exam questions. If it's still confusing, yeah. Obviously, just let me know any questions you have. Okay. Good. Okay. Let's get going. So, question 7. Figure 4 shows two resistors, R1 and R2, connected in series with a battery of EMF 12 volts and negligible internal resistance. Okay, 7a says the reading on the voltmeter is 8 volts and the resistance of R2 is 60 ohms. Okay, so whenever you're given a diagram and then you're given some information and the information isn't on the diagram, I thoroughly recommend drawing it in. Resistance R2 is 60 ohms. It's going to be so much easier to think about if I can see that in a diagram. The reading on the voltmeter is 8 volts. They didn't tell us this in the diagram either. Always annotate the diagram. It makes it so much easier. Okay, good. In 7-part AI, we're asked to calculate the current in this entire circuit. Okay, so there are a few ways we could try to do this. Let's see. So I think what we should do here, there's a few ways of doing this, is realize that we know this resistance. Okay. We know this voltage and this voltage. So it seems like we could figure out this voltage. Let's call it V2. And if we know the voltage and the resistance, we can use Ohm's law to find the current. Okay, so let's have a go. What is the voltage V2 across R2? Well, the EMF that we gain is 12 volts. And Krokovs law says the EMF we gain as we go around here should be the same as the voltage we drop. This voltmeter is saying that there's an 8-volt drop across this resistor. So the potential differences we drop as we go around the loop are 8 plus the unknown thing, V2. It's not a great V. Okay, so straight away we know that V2 is actually 12 minus 8, which is equal to 4 volts. Okay, so this is great news because we know that the current through resistor 2 is going to be the voltage across resistor 2 times the resistance of resistor 2. That's Ohm's law. And we know this is 4 volts and we know this is 60 ohms. So altogether, that's approximately 0.067 amps. And if we have figured out that the current through here is 0.067 amps, that's great because the current through here is going to be the same everywhere around this circuit. And that's what they're asking for, calculate the current generally in the circuit. Well, that's still going to be this. It's the same everywhere. Okay, good stuff. Next question. Calculate the charge passing through the battery. Oh, no, sorry. The next one's over here. 7AII. Calculate the resistance of R1. Okay, good. So we're going to use Ohm's law again. Why? Well, we know the current going through this thing and we know the voltage. So remembering that V equals IR, and let's talk about number 1. So the voltage across number 1 is the current through number 1 plus the resistance of resistor 1. We want to know the resistance. Okay, so it's the voltage across it divided by the current through it. The voltage across it, we're already told, and this is where it's great that we annotated the diagram because we don't have to go back to find a bit of information in the text now. The voltage here is absolutely 8 volts. And the current here, the current is the same everywhere in the circuit. We calculated it here, it's 0.067 amps. Now, if you hadn't rounded previously, if you just had the number stored in the calculator, then that's great because you get a nice round number here. The resistance is actually 120 ohms, but that's what you'll get to 2 significant figures anyway. Okay, good. And then 7III. I actually remember someone mentioning this rule in the chat earlier. Calculate the charge passing through the battery in 2 minutes and give an appropriate unit for the answer. Okay, so we've got charge and we've got time, and that should immediately ring alarm bells that this is something to do with current. Current is the quantity that involves charge and time. Okay, they want us to calculate the charge, so let's rearrange for the charge. Change in charge is current times change in time. They've told us time, 2 minutes. Do we know the current? Yes, great. We already calculated the current. So that's perfect. The current is 0.067 amps and the time is 2 minutes. And what am I missing here? Here I am missing something. It's always important to look out for. I'm missing the units. It's 2 minutes. And we're going to want this in seconds because current is rate of flow of charge in seconds. An amp is a coulomb per second. So, okay, 1 minute is 60 seconds. So we just need to put a 60 here. Altogether, that's how many seconds there are in 2 minutes. Perfect. Okay, so we can log all this in a calculator. And when we do that, we'll get 8 coulombs. And that's perfect. And this is actually why coulombs were defined to be the kind of size that they are. For real life things, like a real life kind of battery, a reasonable human amount of time, a couple of minutes, you now get like a reasonable number of coulombs. It's not some weird standard form, it's just 8. That's great. It's of the order of 1 or 10. Okay, good. So that's why it's a good unit for everyday experiments. Okay, so there's our answer. And there should be some more questions. Yeah, good. Okay, so we're given another circuit diagram here. What are we told? The circuit in figure 3 shows a battery of electromotive force, 12 volts, and an internal resistance of 1.5 ohms connected to a 2 ohm resistor. Should we use non-rounded values for working? It doesn't matter as long as you just keep enough significant figures. You always want to like keep hold of one more significant figure than the one you're like rounding to for that answer. But otherwise you'll be fine. Cool. So when I calculated that current, I'd have remembered that it was probably 0.67 something else, some one extra number. Keeping track of that one extra number should be fine. Okay, circuit in figure 3. Okay, what do we have? Shows a battery of electromotive force, 12 volts, internal resistance 1.5 ohms connected to a 2 ohm resistor in parallel with an unknown resistor. Battery supplies a current of 4.2 amps. Okay, great. So what can we say? Well, first question, 6AI. Show that the potential difference across the internal resistance is 6.3. Now, just be aware, we do not care about the whole story of internal resistances in particular here. As far as we're concerned for this question, it's just some resistor in a circuit. And that's all we need to know. So show the potential difference across the internal resistance, by which they just mean this one here. Show this potential difference is 6.3 volts. Okay, so how can we figure this out? Well, actually, we already know everything we need. The current is 4.2 amps, and that is the same current that's going through here. If you track it back, we have 4.2 amps going in. Perfect. If we know the current and we know the resistance, the potential difference is by Ohm's law, current times resistance. So it's going to be 4.2 amps times 1.5 ohms. Chuck that in a calculator and you should get 6.3 volts. Okay, good. So now in 6AII, we're asked to calculate the potential difference across our 2 ohm resistor. Okay, so let's identify our 2 ohm resistor. Whereabouts is it in this picture? Well, it's just here. Okay, so now we're going to use our Krokovs Voltage Law. Remember, Krokovs Voltage Law told us that we can pick any loop we like, and the EMF we pick up is the same as the potential difference that we drop. So what EMF do we pick up here? 12. Okay, good. What potential differences do we drop? Well, we calculated the potential difference here is 6.3 volts. We just did that here. And what else do we drop? Well, we drop this unknown thing here. Let's just call it V. Well, let's just call it V. Why not? Okay, so we rearrange after using Krokovs law. We get 12 minus 6.3, which I believe should be 5.7. Yeah, 5.7 volts. Okay, good. 6A. Calculate the current in the 2 ohm resistor. Ah, great. Well, let's annotate our diagram. We know this is 5.7 volts now. So how do we calculate current? By Ohm's law, V equals IR. In other words, I equals V over R. In other words, our current is going to be the voltage, which is 5.7. And they've even reminded us that the resistance is 2 ohms. So altogether, check that in a calculator, you'll get 2.85 amps. Okay, and then final question. Okay. Good. So determine the current in R. Well, if we take a look, the current that we're being asked for is this current here. Fine. And let's see what we know. Well, we know this current here now. We just calculated it. It's 2.85 amps. And the thing we're being asked for is this current here. Well, Kirchhoff's current law says the current going in, 4.2, should be the same as the current going out, which is our unknown current, plus 2.85. So altogether, our unknown current is equal to 4.2 minus 2.85. You can chuck that into a calculator and you'll get 1.35, and that's in amps. Good, so that's the final answer to our final question. So let's just round things up. Okay, so what should you now be able to do after today's session? You understand how to draw circuit diagrams and identify components by their symbols. You should understand how energy is transported around a circuit. This was Krokovs Voltage Law. And you should be able to state both of Kirchhoff's law and use them in some big circuit to find the currents, to find the unknown potential differences, and find the unknown EMFs. Perfect. Okay, so hopefully this is useful. I'll look out in the chat for if anyone's got any questions. While I'm looking out in the chat, we have a couple of minutes, so I'm just going to mention, if you're interested, if you enjoyed this, if you found it useful, back in Easter, we did a 2-day physics session, although we also did 2 days of chemistry, 2 days of biology, 2 days of maths, but those were with other tutors. I did a 2-day physics session, and it was an A-level exam crash course. Okay, so there was one for the AS year, one for the A-level year, and it was all about getting exam ready. So if you're interested in this, whilst it's happened over Easter, this is something for which you can still buy the recordings. So, okay, what did we cover? Just to let you know what we did. We covered exam technique. We covered what we think are the trickier topics in the A-level syllabus. And also we had our own revision/seminar booklet that was a part of the course. So just to let you know a bit more about this. Okay, let me just read this question. How hard can the Kirchhoff's questions get, or how complicated? I can't say for sure. I definitely can't make any promises. I think these were a normal kind of hardness, but I don't think that's probably not a useful answer. Sorry. I haven't seen them get much more complicated than this, but it's been a little while since I saw one. So yeah, sorry, I can't answer confidently on that. Okay, so going back to this, what did we do? I said there was these 3 parts: technique, trickier topics, and the seminar booklet. So in terms of exam technique, this is kind of a funny one. We actually spent a serious amount of time just talking about how to break down and understand questions to identify what we call kind of command words. There's basically a lot of structure in exam questions, and we spent a lot of time picking apart that structure to make us better at figuring out what the examiner actually wants from us. We looked at a range of the kind of question types: describe, explain, state. There's loads of them actually. And we went through a load together, not really thinking too much about the content, just about the structure of our answers. Okay. And then, of course, once we'd done that, we started actually doing the physics. We went through what we think are some of the trickier topics. We revised some concepts from what we thought were the most challenging areas. But because we'd already done this exam technique part at the start, we were able to practice that throughout the day. Okay, so that was great. So if that is something which interests you, then you can go ahead and buy the recordings of these sessions for either the first year of A-level or the second year of A-level. And if you want to do that, you can find them here and see more. Okay, so let me just check the chat. Okay, so have I seen these laws used in context to do something in real life? So I would say that I'm very confident that they get used a lot in real life. I haven't personally been involved in that. So in particular, it's really important to know how much voltage there's going to be across some component when you're putting together a circuit. I mean, for instance, to set up the electrics in a house, it's really important that the person who designs that knows and understands how much voltage and how much current there is going to be at each point in the circuit. Because, I mean, if nothing else, this is a safety concern. You don't want to end up touching something that passes too much energy through you. But also you want to make sure that things like the bulbs in your house are light at the right brightness. And that's all about figuring out how much voltage is going to be across them. So anything where you're designing the electrics, for instance, for a building, but I'm sure lots of other situations as well. Yeah, so we did all the kinds of exam questions through from like the 1 markers up to the 5 markers, and tried to look for as much common structure and as many kind of categories of question as we could. Okay, great. Hopefully that was useful. I'm actually going to go and do a session over on the StatRevise website now. So I better sign out so that I get to that in time. So I hope that was useful for everyone. Thanks for being really engaged in the chat. That was really useful, helpful for me. And I hope you all have a good week and catch you all next time. Okay, bye.